Okay. We're going to get started. Just double checking a few things, and then I'll get started with the first problem. In the description of this video, you're going to find the PDF file that I'm going to be working off of. I may be able to actually show a visual of what the problem is in between working on the problem, but we'll see how that goes. I'm working off of a slightly different format today, but hopefully this will work out the way that I want it to. So let's get started. On the PDF that you guys can see right there, there were 6 problems that I had assigned to you as a minor. And I am going to be grading those very shortly. For those that did not turn it in, well, unfortunately, time's up, and we'll have to figure out a different system another time. But let's start with number 10. I'm looking at number 10 in regards to petitions. To get a voter initiative on the state ballot, petitions that contain at least 250,000 valid voter signatures must be filed with the Elections Commission. The board then has 60 days to certify the petitions. The group, or a group, wanting to create a statewide system of universal health insurance has just filed petitions with a total of 304,266 signatures. As a first step in the process, the board selects a simple random sample of 2,000 signatures and checks them against local voter lists. Only 1,772 of them turn out to be valid. Now comes the questions, and I'm going to have to label them in order. So this is number 10. You'll see what I'm writing in a moment. And part A. What percent of the sample signatures are valid? Well, let me write out some information that may be helpful in terms of the sample size. I'm just going to write this off to the side for later. But they took a sample of 2,000. They found that 1,772 of them were valid. Out of a population of 304,000, we'll deal with that in a minute. But part A, what percent of the sample signatures were valid? Well, if I'm looking at that, that'd be 1,772 over 2,000, very straightforward, which is approximately 88.6% if you did that correctly. Part B. I'm looking at part B. Part B says what percent of the petition signatures submitted must be valid in order to have the initiative certified by the Elections Commission. They need at least 250,000 to be certified. Out of 304,266 signatures submitted, let's see, they need at least 250,000 of them to be, what's the word I'm looking for? To be certified. If you calculated that correctly, you get 82.2%. Now, obviously, these problems were a bit more straightforward than some of the other things that we're dealing with. I just gotta turn off. There it is. My phone is on vibrate for some reason. Don't know why. But let's talk about part C. A and B are fairly straightforward, just reading it properly. Part C. What would happen if they committed a type 1 error? Part D. What would happen if they committed a type 2 error? Now, in order to properly understand what the type 1 and type 2 error would be, we need to look at what our null and alternate hypotheses would be. A type 1 error would be rejecting the null hypothesis, and then ultimately saying that there's evidence for the alternative. A type 2 error would be failing to reject the null hypothesis. Errors meaning that you were wrong in the decision that you were making. Type 1, you reject the null even though it's true in real life. Type 2 would be failing to reject the null even though it's false in real life. For this, my null is going to be p equal to 0.822. This percentage, or less, would mean that they didn't meet the criteria, meaning nothing's going on. No steps have to be taken in terms of the petition that they're putting forward. The alternative, which this is the sample, this is the p-hat that they have evidence of. The alternative being, no, they actually have more than 82.2%. This is the null and alternative that you have to keep in mind for parts C and D. You can't see what I am writing. I didn't switch that back over, but that's what I wrote right there. Your null hypothesis has to be p is equal to 0.822, meaning nothing's going on. The petition doesn't have to be filed. There's not enough evidence to show that they met the minimum criteria. The alternative being, no, they did. They met it. They exceeded it. They have evidence to show that they did. The evidence is this 88.6%, which we'll deal with in a moment. Type C. A type 1 error would be rejecting the null even though true. Now, to put that into context, because you need the context to do it, you would be rejecting the 82%, meaning you would say, no, we decide that they have met the criteria. Decide criteria met for, and let me just double check what the wording was on that. There it is. Criteria for certification. Criteria met for certification even though they really didn't. What's written above this line right here is the definition of type 1 error, and what's written underneath of it is the contextual statement that you could make. For part D, I'm talking type 2 error. Type 2 error is you fail to reject the null even though false. You are failing to reject the null hypothesis even though the null hypothesis in real life is actually false. Now, what that means in context, you decide the criteria is not met for certification. Certification. I don't know how to spell whatever. Certification. Yeah, it's totally misspelled. Both ways. Certification. Math teacher here doesn't know how to spell. You decide the criteria is not met for certification, even though it really is. It really has been met. That's what I would write for that thing. I know, Katie. I'm switching back and forth. Don't you fret. There may be a little bit of a delay on what I say versus what you see. I'm sorry, not that. Not what I say versus what you see. Versus what I see, I guess, or something like that. I don't know, whatever. I'm working on a new system. I'm trying to work on the system where I can actually switch between screens instead of you guys only seeing this to make it a bit more fluid. But this is the first time I'm trying this, so I'm still working out the kinks. No worries. Let me switch back Actually, let me try this. Maybe I can do it this way. Da-da-da-da-da-da. Can I see the chat still? Yes, there's the chat. Okay, cool. All right, again, working through the kinks. I can see the chat live, and I can see my screen live. So hopefully, this should work out considerably better. Yeah, that should work out better. So if you do have questions while I'm going over this, please put them into the chat, their question. I may have disconnected, reconnected somehow. It's such a weird thing. I hate the internet so much, but I love it at the same time. Whatever, we'll figure this out. Anyway, if you reject the null hypothesis, you are basically saying, yes, they met the criteria for certification. If you fail to reject the null hypothesis, you're saying, nope, they did not have enough evidence to show that they met the criteria for certification. So, the question, you can see here in part E, does the sample being, and I wrote this out earlier, I'm going to rewrite it again, the sample being 1772 out of 2000, which was approximately 0.886. There we go. Hopefully this will be a bit more fluid. Is that sample enough evidence to reject the null and say, yes, they did meet it? I don't know. Let's just see what happens. Now, if I'm going to run this, this would be a one proportion z-test. One proportion z-test. I'm going to have to meet the assumptions and conditions. Now, instead of writing them, I'm just going to verbalize them a little bit. First of all, random sample. Yes, it says simple random sample. 2000 is a large enough sample size. 2000 is also less than 10% of the population being 304,000 and change. You could say that whether or not somebody signs the petition is independent of the next person. You can even talk about expected failures and successes. But if you're going to be doing expected failures and successes, you should be doing it with the 82.2%. And again, you could do that. Why am I even doing that? 2,000 times 0.822, and insert a 1 minus there. You know, so clearly we have more than 10 in each direction. We're allowed to use that one prop z-test. I'll show it on the calculator, and then I'll show it by hand. One prop z-test, 0.822, 1772, divided by 2,000, and alternate being greater than. Let's calculate that thing. There we go. You're getting a p-value of 3.7 times 10 to the negative 14th power. That number is essentially 0. Your conclusion, you reject the null because p-value is approximately 0. And again, I'm not saying it is 0, it's approximately 0. There is enough evidence to show the petition met the minimum requirement for certification. And I can spell it, certification. There we go. Now, if you don't have a graphing calculator at home, and I'm going to show you how to do this by hand in a moment, but I wanted to show you something else, because again, I got all these fancy features set up for this live stream today. I'm very excited about them. But if you don't have a graphing calculator, there is this website, and I should include the link in a moment. I'm going to cut and paste the link into the description of this video if you give me a moment. But this guy's at the University of Iowa, and he's a nice guy, actually. I just emailed him the other day because his website, one of the links was not working. I'm typing, there it is, save, boom. If you refresh your stream, then you will see the link, hopefully, that I just put in for the Matt Bognar website. And this Matt Bognar website is pretty nice. Let me double check my description here. Yep, there it is. It's a pretty nice website. And you can see on my screen right here that I am going to, there it is. I'm going to go down to Inference for P, and it's going to take me to this screen. Now, I'm zoomed in a little bit, obviously, so you may not be able to, you may not have the exact screen that I have, but this is pretty much what I have here. It's kind of nice. And what I'm going to do with that is I'm going to put in some information. Now, first of all, the sample size, get my keyboard over here. The sample size was 2,000. Now, if you notice when I click that, it does give me X or P hat that I could type in. You could type in the P hat, which was approximately 0.822, or you could put in an X, because this X was 1772. Now, it says inference method. Don't worry about that. Just leave it as what it is and hit enter. And not only, it calculates automatically a 95% confidence interval. You could change that if you wanted to, but that's not what they wanted. What we were looking for was comparing the 0.822, there it is, but we were looking at it being greater than. Boom. And they even give you a significance level for alpha. And you can see the p-value that he's calculated here is pretty much 0. I mean, it was 3 times 7 times 10 to the negative 4. He only gives it to you. Trying to reconnect. I think we reconnected. Man, this thing is weird. Why does it keep disconnecting? Whatever. You could do normal CDF, the sample size, or better. In this case, we had 1772 over 2,000, comma, big number, assuming a mean of 0.822, which was that 250,000 number. I'm actually going to type this in exactly as I write it here, just for the fun of it. It's going to be rounded. Whatever. But then I'm going to have to type in the square root of PQ over N, which in this case, I'm going to have to do the decimals here. 0.822, 1 minus 0.822, over the sample size of 2,000. Let's see what we get. Because obviously the number that I have up here, I should be getting again. Normal CDF, 1772 divided by 2,000, comma, some big number, comma, that thing, comma, and I'm going to have to do the decimals here. 0.822, parentheses 1 minus 0.822 divided by 2,000, chapow. Now, my number is a bit rounded. The reason why it's a bit rounded is because of that 0.822 number and the 1 minus 0.822. I tried to be as accurate as possible. But I got a number that was, what, 2.7 times 10 to the negative 14th power, which is almost exactly the same magnitude that we have up here. It's approximately 0. You would reach the exact same conclusion. Let's look at part F. What could the Elections Commission do to increase the power of the test? Well, you could do a couple things here. If you wanted to increase the power of the test, you wanted to lower beta. To lower beta, you have to raise alpha. Alpha is already 0.05. We could put alpha at like 0.10 if we wanted to. We could put alpha at like 0.50 if we wanted to. It doesn't matter because this p-value was so low, we're going to reject. Our conclusion's not going to change. So, if you're the Election Commission, what do? You increase the sample size. It's probably the easiest way to go about it. Increase sample size, you decrease alpha and beta, your chances of making a type 1 and a type 2 error. As a result, you increase the power of the test. What do we do for the AP test if we don't have a calculator? Good question. Lexi, were you here when I discussed the website for Matt Bognar? If you were not, I would strongly, well, that's a website that I would definitely go to then. Let me switch over to his website real quick, and let me show you what he has to offer. On his website, if I scroll down, I can't really see it. Let me change this screen a little bit. There we go. I'm going to have to put that back in a minute. But on his website, you see right around here, the section for statistical inference. Inference from mu, I'm going to use those a little bit later, but the one that I just used was inference for P. I'm going to have to pull the screen back down. There we go. Yeah. If you look at the inference for P, you can use this to run that one prop z-test. But I've been using random test calculators. What do you mean random test calculators? I'm not sure what you mean by that. Like a calculator that can run a random simulated test, or random as in whatever the heck you could find on the internet? Now, while you're answering that, I could also say if you have an Android phone, and I'm going to type this into the chat, you could also use, mind you, Android phone, WabbitEmu. WabbitEmu is a program that you could, or an app you could download on an Android phone that can download the skin of a TI calculator. Oh, you search t-test calculator. Okay. Okay. Well, and I'm going to do this a little bit later on when we, I'm going to do this a little bit later on, but on Matt Bognar's website, when you see inference for mu right here, the one that I just highlighted, inference for mu, you can use this as a t-test. You can use this as a t-test. When I go over number, where is it? Number 22. I'm going to show you on number 22 how you can get that done. It's really fantastic. You know, stick with me. We'll get them done. Let me just go through these in order. And again, I'm not going to show all of them in terms of like the detailed calculations that you can do. This next one I will, though, number 14. No worries. Let's talk about number 14. Now, I'm going to read number 14, and I'm going to write down some information that I'm going to change the camera. But on number 14, in the depression and heart attack research described in exercise 13, 32%, 0.32 of the diseased group, just writing down this information, 32% of the diseased group were smokers. And if I look back into number 13, the diseased group, cardiac disease, the sample size was 450. Compared with only 23.7% of those free of heart attack. So I'm going to show you what I'm writing in a moment, and that sample size was 2397. There we go. So let me show you what I just wrote down. This is the p-hat of the diseased group, 0.32. That's the 32%. And the disease group having heart disease, that sample size was 450. Looking back at number 13, that's where you would get that information from. Those free of the disease, no disease, I put an N there for no disease, was 23.7%. Being smokers, sample size of 2397. Boom. Yes. Then they want you to create a 95% confidence interval. This one I will show you the Matt Bognar website again because it's really fantastic. But they want you to create a 95% confidence interval for the difference in proportions of smokers in the two groups. And then B and C are more analyzing the results that you just got. But let me show you what you could do for this problem. Now, using this information, if you were going to use a graphing calculator, and you were going to do, and I'll show you that right here in a moment. Boom, there it is. If you were going to use a graphing calculator, this would be a 2 proportion Z interval. You have 2 samples, 2 proportion. They want to calculate a 95% confidence interval. Now, the problem that you have is the fact that they want X. They want X for both of them. Well, 0.32 times 450 would give you the X value for the first sample. 450, there we go. And 0.237 times 2397 would give you the X for the second sample. The problem in the graphing calculator is that because this number right here, this X2 is a decimal, it's going to give us an error if we tried to calculate it. There it is. So, the unfortunate thing that you have to do is you have to round that number. Now, because it's 0.089, you could just get rid of the decimal and just leave it as 568. If you did that, it will give you an interval that is approximate. What did I do wrong here? What did I type in wrong here? How did that turn into a 0? Maybe I never typed it. I don't know how that turned into a 0. Boom. It calculates a confidence interval of 0.0367, 0.12938. And then B and C would be interpreting the results of that confidence interval, which we'll deal with in a little bit. First, I want to show you how you can either calculate that by hand, or you can use the Matt Bognar website. Now, to calculate it by hand, if you're going to be doing this, the difference in the proportions, which, well, I'll put D and N here, there we go, plus or minus, because you're dealing with proportions, it would be a Z star, times the standard error, which we'll have to calculate in a moment. It's a little bit weird. I'm going to show you how you could do that. Now, the Z star, if you have the graphing calculator, of course, the Z star is not that difficult to get. It's a 95% confidence. With 95% confidence, you are not capturing the outer 5%, which is split symmetrically, which means it's the 97.5th percentile. I'm going to show you a couple different ways you could do this. I actually have another screen. Wait, do I have that screen up still? I don't know if I do. Oh, I do. No, I don't. Yes, I do. I do. Bear with me. But if I was going to do this, this would be inverse norm 0.975. Inverse norm 0.975, which would give me a Z star of approximately 1.96. I'm going to store that to Z for later. So just for the sake of argument, the variable of Z is now equal to that exact number. What if you didn't have this? Well, check this out. Let me get to the right screen here. This is something that I haven't shown in the past, mainly because, well, there it is. We didn't really need it, per se. But this is a chart that they give you on the AP test. Now, in terms of this online AP test, they may just insert this in terms of a formula sheet that you can access, but it's actually fairly simple to use. Now, if you look at the left column, the left column is giving you the particular Z-score that you're looking for. The top row is giving you the second decimal of the Z-score that you're looking for, the Z-star that you're looking for. It's actually fairly straightforward to use once I show you what we're looking for. Now, they give you this chart, which is everything in terms of negative z-scores, and they give you the second chart, which is everything in terms of positive z-scores. The positive z-scores is where we're at, because look at the middle. We're looking for something that is 97.5%. 97.5% right there. I just highlighted it. It's a really weird chart, but it's kind of worth it if you don't have a graphing calculator. Looking at that chart, I have the 97.5th percentile. And if you look far to the left, 1.9. And if you look all the way up to the top, 0.06, 1.96 is the z-star that you're looking for. This is how you could use this chart. It's pretty ridiculous. Maybe I'll show you that for something else a little bit later on. But it really depends. It depends on what confidence level you're looking at. We were looking at the 95th confidence interval, 95% confidence interval, so we needed 0.975 to put into inverse norm. It's very strange. Regardless. Let me jump back here. Now, if I were to calculate the difference between these two decimals, it'd be 0.083 plus or minus 1.96 times some kind of a standard error. Now, this standard error has to be the combined standard error of these two separate samples. We do not know the population P. We're trying to capture the true P, the true difference between these two. So we would have to do something crazy like this, where it was like 0.32 times 0.68 over 450 plus 0.237 times 0.763 over 2397 with a giant square root around the whole thing. That's just ridiculous. Basically, if you were to calculate the individual standard error, it would be p hat q hat over n with a square root around it. Same thing for the other one. But to combine them, you'd have to square them to variance, add them together, square root them back. And again, Matt Bognar's website's probably going to be a bit nicer here. We'll deal with that in a little bit. Square root 0.32, 0.68 divided by 450 plus 0.237, 0.763 divided by 2397. Boom! There's my standard error. Let me store that to S. So if I'm going to calculate this confidence interval, it would be 0.083 minus the z star times S and plus the z star times S, which is exactly, those bottom two calculations are exactly the interval that we have up here. And again, I don't see that many people doing this on a free response. This is mainly needed for if you had to do a bunch of multiple choice questions, which, huzzah, somehow this year, you lucked out. Let me jump to Matt Bognar's website. Again, if you don't have a graphing calculator, I would pick Inference for, and you can see it right there, Inference for P1 minus P2. If you click that, there we go. If you click that, then they give you everything that you need to type in. It's actually fairly straightforward. Again, the Matt Bognar link is in the description. But the first one was 450. That was 0.32 because they're asking for P hat. 2397. 0.237. Hit enter. Boom, right there. Confidence interval. 95%. And it's the exact numbers that we got. Well, not the exact numbers we got. Probably a bit rounded. Now, if you notice right here, they only give you options for the 80%, 90%, and 95% and 99% confidence interval. That's all that they really give you, unfortunately. But then you could, if you wanted to, perform some kind of a statistical test here. But they do give you the confidence interval for the difference, which is really, really just nice. Now, regardless of how you get it, this is the confidence interval that we're dealing with. Let's look at the last couple questions. Oh, where are my questions at? Oh, right, my questions are on this screen. There we go. So for part B, is this evidence that the two groups in the study were different? Is this evidence that the two groups in the study were different? Well, for part B, yes. Yes, this is evidence to show that the two groups are different. The reason being, 0 is not in the interval. The true difference between the two groups of those diseased and those not diseased, the true difference between them is something that is between approximately 3.5% and almost 13%. Meaning there's a positive difference. Well, we're 95% confident that there's a positive difference no matter what. So this is evidence. It doesn't prove it, but this is evidence to show that the two groups are indeed different. If you wanted evidence to show that they were not different, then 0 should be in the interval. But it's not. Part C. Could this be a problem in analyzing the results of the study? Yes. Absolutely yes. Reason? Smokers. Smokers. Talk about smokers? Come on. 32% of the disease group are smokers. 23.7% compared to 23.7% of the those with no heart disease were smokers. If you're talking about smokers, this is a confounding variable because smoking immediately affects your body. Yes, it mainly affects your heart, but it could definitely affect your cardiovascular system. It's a confounding variable. Anywho, let's look at number 20. Scroll down a bit. There we go, number 20. Flip this screen back. There we go. Now for number 20, we're still dealing with proportions. In number 22, we're going to be dealing with that T, which I'll show you in a little bit. For number 20, I'm not going to go into the full details of the formulas. I will verbalize a few things, but I'm not going to go into the full details just yet. But we'll see how it goes. It's number 20. Some people fear that differences in insurance coverage can affect healthcare decisions. A survey of several randomly selected hospitals found that 16.6%, I'm going to write some of this information down as I'm talking about it, of 223 recent births in Vermont, Vermont, involved cesarean deliveries, compared to 18.8% of 186 births in New Hampshire. There we go. Is this evidence that the rate of cesarean births in the two states are different? This is a 2 sample. I should say, more specifically, a 2-prop-Z test that you're going to want to be using for this problem. A 2-prop-Z test. They're 2 independent samples, one in Vermont, one in New Hampshire. They're both random. 223 and 186 are large enough. Since there is no population proportion or population difference between the two, you could potentially look at the number of successes and failures from Vermont and New Hampshire, meaning like 0.166 times 223 and 1 minus 0.166 parentheses times 223, just to show, what did I mistype? I didn't put a parenthesis there. There we go. Just to show that they're both greater than 10. You could do that for New Hampshire as well. And again, you have to run through the assumptions and the conditions. Your null hypothesis would be that there is no difference. There is no difference between the two. Nothing going on. Nothing unusual. Your alternative is that there is a difference between the two. Now, if you read the question carefully, notice I left that blank for a moment, but But if you read the question carefully, number 20, is this evidence that the rate in the two states is different, not that one is greater than the other? So it has to be not equal to. Let's just suppose you went through your assumptions and conditions. One person getting a cesarean birth is independent of another person getting one. The two samples in general independent of each other. They're both randomly collected. Less than 10% of the population of cesarean or of births in general. All that other stuff. And let's say you ran through the 2 prop Z test. I'll show you that on the calculator, and I'll show you that on Matt Bognar's website. 2 prop Z test. Now, again, I have to do X and N here, unfortunately. Oh, I can't, yeah, 0.166 times 223, which is a decimal. I'll fix that decimal in a moment. 0.188 times, nope, times 186. I'll fix that decimal in a moment, and it's got to be not equal to. Unfortunately, with the graphing calculator, you have to go without these decimals here. I'd probably round that up to 35. Calculate. You get a p-value of 0.5563 is what it rounds to. 0.5563. Now, again, if you were going to do this by hand, this is a bit cumbersome to do this one by hand. I'm not going to show you the full calculation of it by hand, because that would be crazy. But if you were going to do it, you were going to be looking at the difference between these two. Now, the difference between these, if you did that in this order, 0.166 times minus 0.188, it would be a negative number. So it would have to be small number, comma, whatever this difference is. Yeah, negative 0.022, getting that difference or smaller, or lower, assuming no difference and a combined standard error. Now that standard error would have to be a pooled standard error because you're assuming that there is no difference between the two, which is why the hand calculation of this thing would be incredibly cumbersome. But if you're doing it on the graphing calculator, you can get that p-value, which that p-value is way too big. You would fail to reject the null. You would conclude that there is not enough evidence. There's probably not any evidence considering how big it is, but there's like little to no evidence showing that there's a difference between the two. There's enough evidence to show that there's no difference between the two. Evidence to suggest, that is. If you were doing Matt Bognar's website, Matt Bognar's website's pretty sweet for this. Because of what he already has. 223, 0.166, because you can type in that p-hat. Put an extra decimal. There we go. Come on, you. 186 for the second sample. 0.188. Again, I put an extra decimal. Don't know why. Hit enter. It calculates the confidence interval. Now, again, that's not what they wanted. They wanted you to actually perform the hypothesis test. You need to get an actual p-value. We're going to get a p-value approximately equal to the 0.5563 that we got before, because this one's going to do it exact. Null hypothesis, there is no difference between the two. Boom. Right there. Because we're doing not equal to for the alternative, it's a two-sided hypothesis test, meaning they would double the p-value of that normal CDF. I actually should write that. But you can see that it gives us 0.5623, which is approximately close to what our calculator said. The reason why our calculator was off is because, well, we weren't allowed to type in those decimal numbers into the 2 prop Z test. We had to round them. As a result, our p-value is also rounded. But the conclusion remains the same, which, by the way, I should write that here. It should be 2 times, because it's two-sided, it's two-tailed, it's not equal to. Let me go back to the question here. Is this evidence that the rate of cesarean births in the two states is different? No. With a p-value of 0.5563, we fail to reject. We have enough evidence to show there is no difference. Or we have evidence to suggest that there is no difference. Fluffy language. Let's talk about number 22. Number 22. Let me make sure I got the right screen up here. There we go. A college student is on a meal program. His budget allows him to spend an average of $10 a day for the semester. He keeps track of his daily food expenses for 2 weeks. The data are given in the table. Is there strong evidence that he will overspend his food allowance? Explain. Okay. Well, I'm going to have to type some of this information into my list in order to get an average and a standard deviation. Unfortunately, if you don't have a graphing calculator, you have to use some kind of weird website to do this, I guess, because you need that sample standard deviation. You could try to calculate that sample standard deviation by hand, but that's not very helpful. It's very cumbersome to calculate a sample standard deviation by hand. I'll have to find a separate website as to how to actually learn how to do that information, to be able for a website for you just to type junk in for you just to calculate that sample standard deviation. But this problem is going to involve a t-test. The reason that this problem is going to involve a t-test is because you do not have a population standard deviation. You don't. You do not have a population standard deviation. Now, if you notice, I typed in all of my data into my L1. I could run a 1var stat. What's nice is that with the graphing calculator, you can actually run the t-test from the list itself, but I'll show you that in a little bit. This is number 22. I got an X bar of approximately 11.42. I have a sample standard deviation of approximately 8.06. Sample size of 14. That looks about right. Now going back to the question itself. Is there strong evidence that he will overspend his food allowance? His food allowance is $10 a day. Null hypothesis. Mu is equal to 10. They're looking at him overspending. So the alternative is mu being greater than 10. Okay. Now again, running through your assumptions and conditions, going back to the problem real quick, there we go. You don't have to worry about a large enough sample for t-testing, but we had to make sure that there was a random sample. Keeping in mind, he just kept track of 2 weeks worth of his daily food expenses. It's reasonable to say that his food expenses from one day to the next are random and independent of each other. That's fine. 14 days is less than 10% of his yearly food buying, I guess, at this semester. I mean, yeah, if he's spending, and you're looking at one semester, what's September, October, November, December, 120 days, 130, 140, yeah, I guess it depends on what you count as a semester. Oh no, the semester goes from August to December, my bad. That's like 150 days. Yeah, so it's definitely 14 days is less than 10%. But you also have to look at the nearly normal condition. And again, on a graphing calculator, it's a lot easier to do this. Otherwise, you'd have to do it by hand. Boom. Zoom 9 it. Ugh. The nearly normal condition. You got to make sure you mention it. This does not look normal to me. We're still going to proceed with the test. But definitely make mention of the fact that the nearly normal condition's iffy. Definitely iffy. I mean, you could say, like, but whatever. Kyle, because I'm a genius. That's how I did that. Also, yes, you're very late. Anyway, back to this. So, assumptions, conditions, make sure you make mention of them in regards to whatever test you're trying to do. We want to do a one sample t-test, which I'm going to show you how you can do using the t-test in the calculator, using tcdf in the calculator, and by using the Matt Bognar website. So, if you were going to do the t-test in the calculator, you could do data, and then it does L1 like that. You just got to make sure that you set your mu to be 10, and we want it to be greater than. If you didn't, you could hit stats, and then you'd actually have to type in that stuff, which is nice because since I already did the 1var stat, it automatically inputted that information. But again, greater than. Let's see what this thing calculates out to be. Actually, no, let me draw this one. Just see what happens when I draw it. Oh no, I have stuff typed into my y equals key. Like a jerk. Oh, no! Sorry, my plot is still there. There we go. That's why that thing did that. That's why I don't draw things. Now we're going to draw it. And it should give us the proper p-value. P-value of approximately 0.26. If you run that, you get a p-value of approximately 0.26. That's using the calculator function. Now, let's just pretend that you had a tcdf to work with. If you wanted to do a tcdf, you're going to have to calculate a t-score. 11.42 minus 10, sample data minus the population data over sample standard deviation over the square root of the sample size. This should give us our t-score. I'm going to show you how you can use tcdf to get that thing done. No, you can't see it. Whatever, I'll type it in first. 11.42 minus 10 divided by 8.06 divided by the square root of the sample size. Chapow. You get a t-score of approximately 0.659. Nah, I can go 0.66. Yeah, why not? Approximately 0.66. If you were going to go tcdf, you would go 0.66, comma, big number, comma, the degrees of freedom. And it gives us a p-value of approximately 0.26. But again, not a lot of people are going to do that. Not at all. If you're on the AP test, it is perfectly acceptable to just be like, well, I used this particular website, the Matt Bognar website for inferences from mu or some junk like that, because I want to show you visually what that would look like. So on the Matt Bognar website, let me go back here real quick. Here we go. There is this thing right here, inference from mu. Now, I guess there's an updated beta version. Use whichever one you want. It really doesn't matter. But it's inferences from mu. Where'd you go? There you are. Can I close these? Ooh, I can close those. Good for me. Inference from mu. If you click that, you can type in your sample size. You can type in your X bar. Now again, it does give you an option for S or sigma. If you leave it as sigma, that is a Z test. You're going to want to pick S because this is, there we go, this is a sample without the population standard deviation. If you do that, now sometimes this happens. Sometimes like the little weird thing here where like the formatting is messed up on this. I found that if you just refresh it, sometimes it does work. Nope, didn't work that time. Come on, you. Inferences from you. If it doesn't work this time, I'm going to try the beta version. Ah, it worked this time. Sometimes that happens. Now you can see, look, it calculated a 95% confidence interval for you. We're going to want to type in 10. But now, mind you, we're going to have to do greater than. So I got to change that to greater than. Chapow. And looky, right there. There's your p-value. 0.26. 0.26. If you were going to be doing this on the AP test, you would have to write out your hypotheses, state your assumptions and conditions, state that you used a website or something along those lines to run the proper inference test or hypothesis test, and you producing this p-value. Then you can write out whatever conclusion that you were supposed to be writing out. Now, for this problem, because the p-value is so large, we fail to reject null because p-value is greater than 0.05. There's not enough evidence to show he spends more than $10 a day. There's not enough evidence. That's how you do number 22. Now, I definitely want to talk about 26 and 28. 26 and 28 are dealing with two sample. Let me flip the screen over to them. There we go. And there we go. I'll probably spend more time at number 28, but let's just talk briefly about number 26. At the middle of the 2016-2017 NBA season, James Harden led the league by making that many free throws. Okay, cool. Let me just write this information out for number 26 while I'm reading it to you. So p-hat for Harden was 468 out of 544. The percentage is one thing. But I know that if I'm going to be doing the two-prop z-test, I'm going to have to type in X and N. And the p-hat for Westbrook was 425 out of 5. Yay, I think it reconnected automatically. Anyway, so if I'm going to be running this, let me jump to my calculator. I'm going to be doing a two-prop z-interval for the differences, and knowing what I had to type in there, 468, 544, 425, 517, and they wanted a 95% confidence interval for the differences between the two. Chapow. We get negative 0.0058 and 0.08224, meaning the true difference between Harden and Westbrook, or I'm sorry, I'm 95% confident that the true difference between Harden and Westbrook is within that interval. The true difference. The current difference is like a little less than 4%, but that's sample. That's one season sample, or one season's worth of samples. So, this is what we got. What does the question ask now? Find a 95% confidence interval. Got it. Based on that confidence interval, is it certain that Harden is better than Westbrook at making free throws? Answer, no. It's not certain. Not certain because 0 is in the interval. Meaning, since 0 is in the interval, it means that 0 is a possibility for the true difference between the two, meaning there is no difference. We're 95% confident that the true proportion is in that interval, and since 0 is in that interval, that's a possibility, and we can't exclude it. So no, we're not certain that Harden is better than Westbrook based on this sample. Maybe if we looked at different seasons, maybe if we looked at different samples, who the heck knows? Let's talk about number 28. Change my screen over. Oh, before I talk about 28, let me go back to, here we go. Let me go back to Matt Bognar's website. because if you look at inference for P1 minus P2, and you type in the appropriate information, 468. Now, the unfortunate thing is you have to type in a p hat sub 1, which I have here as 0.86 based on the problem. And the other sample, oh no, that wasn't 468, that was 544. There we go. This one was 517, and based on the problem that they gave you, 0.822. Hit enter, and it calculates a confidence interval. Now, it's not the exact same confidence interval that we just got. It's an approximate confidence interval for 95%, but 0 is still in the interval. And because of that, we cannot be certain that Hardin is better than Westbrook. So, let's look at number 28. On number 28, last problem of the day. Several programs attempt to address the shortage of qualified teachers by placing uncertified instructors in schools with acute needs, often in inner cities. In a 1999 to 2000 study compared students taught by certified teachers to others taught by uncertified teachers in the same schools. Reading scores of the student certified teachers averaged 35.62 points. So hold on. Mu of certified teachers was 35.62 with a standard deviation. I don't know why I just wrote mu. I wrote mu. This is a sample with a sample standard deviation of 9.31. Okay. Cool. Then the scores of students instructed by uncertified teachers had a mu of 32.48 with a sample standard deviation of 9.43. Both had sample sizes of 44. The appropriate T procedure has 86 degrees of freedom. Now, that piece of information would be needed if you were doing a TCDF, which I will show you what you could do in a little bit. In a little bit. Is there evidence that... wait, I lost my place. Is there evidence of lower scores with uncertified teachers? Discuss. Here's what I wrote down. X bar of certified teachers, X bar of uncertified teachers with their appropriate standard deviations and their sample sizes with 86 degrees of freedom. Now, your null would be there is no difference between the two. Your alternative, because of the way they worded that question, they worded the question, is there evidence of lower scores with uncertified teachers? Meaning certified teachers had a higher score. This is a 2-sample t-test that we're going to want to run. Now again, you'd have to run through assumptions and conditions. Sample sizes being less than 10% of the population. It's a random, was it random? Let me double check that. Bow. Reading scores of students of certified teachers average that and that. They don't specify, do they? Several, it's at a study comparing those. It doesn't say that they're random. It says there are 44 in each group. It's a study, so I guess that they were randomly placed or something along those lines. That's crazy. Yeah, but again, assumptions, conditions, a lot of that can be touched upon, talking about random scores or each student's scores independent of the next, less than 10% of the student population, or the teacher population, I should say, or something along those lines, certified versus uncertified. Unfortunately, you can't even talk about nearly normal because they don't give you enough information. But you could just say something along the lines of, you could say something along the lines of, there's no reason to believe that it's not normal. But again, assumptions, conditions, that whole deal. I'm going to show you what you would do in the calculator. I'm going to show you what Matt Bognar's website could do, and I could show you what you could do by hand. Actually, you know what? No, let me start with the by hand first. If you're going to do this one by hand, 35.62 minus 32.48 gives you a difference of 3.14 in the sample. If you're going to calculate a t-score, sample difference minus the assumed population difference over, now this would be a combined standard error. The standard error would be sample standard deviation divided by the square root of the sample size. But in order to combine them, I would have to square it. So hold on. The standard error of this one would be 9.31 over the square root of 44, and the standard error of this one would be 9.43 over the square root of 44. In order to combine them, I would have to square both of them, then add them, then square root them back. If I were to square and then add them, and then square root them back, that's what it would look like. This gives you an approximate t-score of, I wrote down 1.57. Let me double check the calculator. 3.14 divided by the square root, 0.31 squared divided by 44, plus 9.43 squared divided by 44. Chapow! Yep, 1.57. That's your t-score. So, if you were going to do TCDF, it would be 1.57, comma, big number, comma, degrees of freedom. The combined degrees of freedom. Unfortunately, to do this one by hand, the combined degrees of freedom by hand is much too complicated for a high school AP stat class. The formula's in the book, but even the book's like, just use something else to get it. 86 degrees of freedom. If you were going to do that, TCDF, 1.57, comma, big number, comma, 86, chapow. There we go. We get a p-value of approximately 0.06 and change. I want to use the exact number. TCDF, that answer, comma, big number, comma, 86. I like that one better. 0.0598. Yes, I know it's 0.06 still, but that's my p-value. Now, because of that p-value, we run into a little bit of an issue. With that p-value. I'll explain why in a moment. But that p-value is going to give us a little bit of trouble. Yes, we would fail to reject at the 0.05 level. But I need to talk about that because it's so borderline. But again, this is what the conclusion's all about. Now again, let's say that I was just going to use the t-test here. I'll write down some other stuff later. Oh yeah, this is what I wanted to write down. I got a p-value of approximately 0.0598 using TCDF 1.57, comma, big number, comma, 86 degrees of freedom. Let's run a two-sample t-test. 35.62, 9.31, sample size of 44. 32.48, 9.43, 44 sample size again. Greater than is automatically set. Don't worry about pooled. Calculate that sucker. It gives you the exact p-value that we were just talking about. The exact p-value. That's cool. What if you were using Matt Bognar's website? Again, Matt Bognar's website's a pretty sweet website. If you were using Matt Bognar's website, we would go to Inference for mu1 minus mu2. And you would type in the appropriate information. In this case, 44 is my sample size. Make sure I got this. 35.62. It's a sample standard deviation. Come on, you. You might... There it goes. Yes. Okay. 9.31, 44, 32.48, 9.43. Now, this one right here, the assume the sigma is equal to sigma, the population 190, that has to do with it being pooled or not. Just leave it as is. It's not going to make that much of a difference. I do have to select the one for greater than there, and there being no difference, and there being a difference. Boom. Look at that beautiful number right there. Just a gorgeous number. 0.05984. Look what happens if I change that assumption right here. It gets you the exact same answer. It doesn't make that much of a difference in these examples, so I just wouldn't worry about it. And look at that. 86. That's the degrees of freedom. America. Now, the conclusion. It's the most important part. Let's see here. Boom. Hey, look, there's Omar. The conclusion. It's the most important part of this whole thing. Now, on your minor, I'm not going to expect this detailed of a conclusion. What I would expect from most people is the p-value is greater than 0.05. We fail to reject null. There isn't enough evidence to show, and again, I want to put this into the context of what the problem is actually saying. The problem's asking, is there enough evidence of lower scores with uncertified teachers? There is not enough evidence to show that uncertified teachers produce lower scores. There's not enough evidence. That's an appropriate conclusion. The details that I have to get into is that this 0.0598 is so close that you can do this and you'd be fine. But 0.0598, 0.06 is less than 0.10. You would reject at an alpha level of 10%. But you would fail to reject at an alpha level of 5%. Again, if you wanted to get a little bit more detailed about it, and they may ask you about this in the future, but if you wanted to get a little bit more detailed about it, you could say something to the effect of, well, we would fail to reject at the 5% level, meaning there's not enough evidence, but there is enough evidence at the 10% level. And that would be something that would be appropriate. Now, again, if we have any questions in regards to these problems, I'd be more than happy to answer them. If you shoot me an email, if you leave a comment in Google Classroom, and there's Omar with a comment as well. Sorry, I lost my train of thought because I was reading that. Yeah, Omar, stats in college is a bit weirder. But no, I'm not going to get into those conversations right now. But anyway, let me wrap this up, and then I'm going to shut this down because I gotta work on other stuff today. But those minors should be graded for you soon. And stay tuned. I have another video that I'm going to be uploading soon in regards to T-Star. No, Omar, you're not in my Google Classroom for this semester. How about, Omar, if you have any stats questions, you can leave a comment after I've ended the stream or something like that. And that would be appropriate. Oh, goodness gracious. I've been in this stream too long. It's almost been an hour and a half. Anyway, Everyone remember to subscribe. Click that notification bell. I'm going to sign off here in a moment. Once I can actually get this thing to stop. There it is. I'll stop streaming. I need a cup of coffee. I'll see y'all later.